I'm going to turn on the pencil. Let's see. Is the pencil on? Nope. Turn on the pencil here. Where's my pencil? Right here. And let's make sure it's wide enough. Let's make it a little wider to see. And thickness of my pencil. There we go. Okay, going to do some practice. Inverse problems. So we're going to practice our inverse. Practice inverse. So go ahead and put your name at the top of that practice paper. If you don't have one, grab a blank sheet of paper, pass one down from the end. Let's just do simple, start simple, and get hard. Let's see here. Suppose I have a function f of x equals, let's do 2x plus 1. How do we find the inverse? Well, remember f of x is like saying y equals 2x plus 1. Switch x and the y, so we turn that to 2y plus 1 equals x. So we switch the x and the y, so I'll put a little notation there. X gets switched with y. Now we solve for y. And do careful steps through. Step 1, what do? Subtract 1 from both sides. 2y. Oh, let's make the notation here. We can say, okay, I'm going to subtract 1 from both sides so I can have the 1 come over here by the x. And we're getting y closer to be by itself. So we subtract 1 from both sides. We can do that and maintain the equality. So 2y equals x minus 1. Now I want to get y by itself, so I need to divide everything by 2. And 2y divided by 2 gives you y. Therefore, the y equals x minus 1 over 2. This is the answer. This is our f inverse of x. Does that make sense? I can go slower. We'll do another one similar. More practice. Let's do another one. Let's see. Let's do one. How about this one? This looks scary, but it actually turned out pretty easy. Let's say f of x equals 1 over x plus 3. So y equals 1 over x plus 3. Doesn't come to mind right away. What do? Let's see. We're dividing by x, adding 3 to it. Well, let's just crank it through our formula. So first of all, switch the x and the y. We get x equals 1 over y plus 3. Well, the first thing we do, before we can do anything, we have to get the 3 out of the way here. So let's subtract 3 from both sides. And now this becomes x minus 3 equals 1 over y. Hey, we're getting closer to getting y by itself. Well, how do I get y by itself now? Yeah, do the inverse of both sides. Think of it turning it upside down. We know if we get 1 over if these two things are equal, the inverse of those things will also be equal. So I can just say 1 over x minus 3 is equal to 1 over y, which we know will be y. Turn both things inverse, and I get my y, and look at that. I've got my inverse. Now, it doesn't look exactly the same. It does have an inverse in there, but I have to subtract 3 from it first before getting the inverse. Is that making sense? Let's just do one more. Not going to be super complicated. Let's throw a little exponent in there. Sometimes those are scary, but just follow our formula. Let's say y equals x squared, and we'll do a minus here. I haven't done minus 4. Remember, those signs can kind of mess us up. Let's do x squared minus 5. So, what do? Switch x and y, and we get x equals y squared minus 5. And just like we did before, you have to get rid of your added things before you can do anything else to solve it. So let's add plus 5 to both sides. So now we get x plus 5 equals y squared. And how do you get y alone? Gotta take the square root of both sides. If you have an equality, you can square root both sides. And the reason I did a square root is because I have a 2 there. Square root of y squared is y. So I get square root of x plus 5 equals y. One little thing you have to make a note of here. Remember, is there more than one possible answer to square root of y squared? There is a plus or a minus. Y, negative 2 squared gives me 4, and 2 gives me 4. So I could to be super proper, I probably would say plus or minus square root of x plus y gives me y. This is a little weird, and that gets back to our issue of the one-to-oneness. Square root. Is square root 1 to 1? What do you think? Square root of 4. What's the answer? Plus or minus 2, right. So square root gives me 2 possible answers. So square root in proper math is not 1 to 1. Normally you say, give me the positive square root. You usually think, yeah, positive numbers make sense. Give me the positive square root. Then it is 1 to 1. But square root as a function is not 1 to 1. So normally they say, well, okay, we go with the positive pieces. Because usually in real worlds, when we're dealing with squaring things, we're squaring positive numbers when we're talking about physics and things that in chemistry. Usually negative means, though, that's the experiment never goes that direction. But in pure math, square root does give you 2 possible answers. And this also can go bad when you have anything smaller than negative 5 for x. It blows up because a negative number square root has that old imaginary thing hiding in there. So that was just a few practice, and that blank worksheet just for me to see that you're doing okay. And you know what? I won't even, I'm not grading it. So if you get on any of these problems and you're a little embarrassed to ask a question, just put a little note there. I'm really having a hard time with this, and won't call you out or anything. I'll try to make sure we cover that. So if you're having any hard times with any of these, just put a little note on your paper. I was really confused by this. Okay, now I want to help you get those quizzes done. I'm going to actually go through some of the problems that are on the Lumen quiz. So let's take, why isn't it coming up to the screen? Come on. There we go. I'm going to help you with some problems on the Lumen quiz. First of all, I'm going to go over this whole one-to-oneness thing. Which one of these graphs is 1 to 1? And remember, in the graphs, turn on my pencil. What's the test? Just do that old horizontal line thing. If I draw a horizontal line and I hit 2 parts, it's not 1 to 1. I don't even have to do the vertical line. So no, this is not 1 to 1. How about this one? I'll change my pen color just because it's not so it's not the same as that graph there. And I have to really do radical changes in color because, man, on the screen they're really not that different, aren't they? Okay. All right, so horizontal line, cross one, vertical line. Yeah, that is 1 to 1. This guy, horizontal line, good. Vertical line, good. This is an example of the square root thing. Square root, if I had a plus and minus, I would expect the curve to go something like that, but they're limiting it to this particular area. You are allowed to have functions that only are defined in certain domains. So yes, this is 1 to 1. If they said, what's the domain of it? I would say, oh yeah, it's starting and it looks like it's, I think it does hit 1 for input, and then looks like it goes on forever for my domain. How about this one? Horizontal line, good, good, good. Vertical line, good, good, Here's the only question, and I guess I can't really tell, but it sure looks like it gets really steep, but never goes exactly vertical, because then it would go to infinity. So I'll say I'm going to call it good, even though I would really want to zoom in on that part to be sure. But I'm going to call it good, because it's really steep, but I'm pretty sure it crosses at only one point. Oh, that reminds me of my trigonometry. Those fun cosine functions. And I love them, and something like sine of theta or sine of t, vibration or something that changes over time, that wheel spinning around. I can see that my teacher drawing those circles every day in trigonometry. But vertical line test passes, but not the horizontal line test. It is not one-to-one, but it's a cool function that's not one-to-one. So sorry. Really cool trigonometry, but not one-to-one. This one here, it does some crazy things, and it looks like it's really, really big, but horizontal line test passes, vertical line test passes. So that is one-to-one. Now, we're doing some simple ones, going to harder ones. If f of 6 equals 9, what is the inverse of 9? Well, if the function starting with 6 got me to 9, the definition of the inverse is if I start with 9, I get back the output that f started as an input. So my answer is always going to be the input x for only that particular point. I don't even know what the function is. I just know when I gave it a 6, I got out a 9. The inverse, if I feed it a 9, if it's really the inverse, it will get me back what got me there. And vice versa. If the inverse got me to negative 6, the inverse given negative 6 got me to negative 5, then I know that the original function, if I gave it a negative 5, it got me to a negative 6. The whole definition of the inverse, if I start with a negative 6, it gets me negative 5. That means the original function, if I give it a negative 5, will take me to 6. So we know that every function, an inverse of the inverse, gets me back to the original function. Some easy ones to work with. Now you give it the table. We just have pairs of numbers. And what's the question? Which table below is the inverse function? Well, before looking at my choices, what would it be? Well, if I start with x and I get y, remember that's the same as f of x. Well, the inverse is going to be I start with this, and f of inverse takes me back to my original f inverse. And the fill-in, the placeholder, if I want to call it x, or some other letter, we'll call it x. But for the inverse function, we're saying these numbers are our input numbers x for our inverse function. So y becomes our input to our inverse function. We know it will take us back to this. So basically, we're looking for a table that is simply these two switched around. Let's see what they give us for possible choices. So first thing I'm going to look for is a 2 for the x. Not even going to look at the others. There's the only one that has a 2 for the x. They gave me a pretty easy one. If I were doing this, I'd be a little more tricky. I'd give you a 2, and then I'd mix these up and have one that didn't match exactly the table. But you can see, this is exactly that table upside down. I'll zoom out a little bit so you can see. It's exactly that table upside down, so that is the only possible answer. It was the only one that had an x input as a 2, so they were a little easier on me. So, one-to-one table. Now, it's going to get a little tougher, but not radically tougher. We have inputs and f of x, and they're going to give us a table for the, they don't even give us the inverse. They just say, well, what's f of 5? Well, input of x of 5 gives me a 6. If I got a 9, what was x? Well, I got an output of 9 there. That must have meant that x was a 6. Something I forgot to do is to check, is this 1-to-1? That's something that I kind of just assumed that they were being nice to me. It wouldn't hurt to check, do I get unique values? Let's see, all x's are unique. Do I get, there's no doubling out here. Just do a quick check. Yeah, it doesn't look like there's anything that got the different value. So I did a quick 1-to-1 check. Looks good. They didn't say to do that. They should probably start out with, hey, is this a 1-to-1 function? Because without a 1-to-1 function, you can't even do the inverse. Don't even worry about trying. F of -1, not F inverse of 6 is, well, what that's asking for is what value of x would give me a 6 in the original function. Well, I got a 6 when I fed it an x of 5. Therefore, inverse function, given it 6, will take me back to 5. If f inverse gives me 6, well, remember, f inverse, let's just write it out here. This is what f inverse would give me if this were my x's. Well, if f inverse got me to 6, give me my original x out, then f inverse, and this is where the confusing part is, what did I give to f inverse to get me to 6? What number got me there? They could have used a different placeholder just because I look for x's. No, it's not those x's. This is my input to my inverse. If I got it, if the output of f inverse was 6, what was the input for f inverse? It would be the 9. This is probably the hardest one because they throw that x in there, confusing you. Think of this as the input to the inverse function gives me an answer of 6. This is my input to my inverse function. Inverse input. These are for the inverse, these become my inputs to my inverse. The x part of the inverse. If I got to a 6, that means my input to my inverse must have been a 9. And let's just do a few more, and then we'll go on to exponential functions. We've done this. Let's practice that whole thing. What do we do? Let's first put it at y equals 3x plus 11. Switch x and the y. Solve for y. Subtract 11 from both sides first. That will get rid of that. And then on this side I have x minus 11 equals 3y. Divide by 3 to get 1y over here. And I get the answer, x minus 11 divided by 3. And once you've done these a few more times, you'll say, oh yeah, to get x, I have to subtract 11 from it. Dividing by 3 will get me back my original x, if I want to have the inverse. But if I want to say my placeholder, my input to my inverse, we'll call it x. Solve for the inverse function. So x minus 11 divided by 3. Remember the video we watched? He did the solve for x and then switch x and y. Either way is perfectly fine. Because remember that y and x, that just means what's the input placeholder letter I'm giving to that input. Okay. We can turn off worrying about inverse functions now. Got a new little problem for you. We're dealing with exponential problems. In the textbook that you have online, they jump right away into rules about exponential functions. I'd like to take a little slightly different path and talk about the meaning of exponential functions to give a hook into what real life, why exponential functions are good to know about. And I have given you the link to this in previous semesters. they gave you these links, and this link is over in Moodle, down in this section. I added this link. It's called OpenStack's Help with Exponential Functions. There may have been a link somewhere in resources, but this used to be our textbook. Now we have PDFs, hard copy, or copies of the PDF files that came from there. But if you go to OpenStack's, I think it might help you understand the whole reason behind using exponential functions. And it has to do with, the first problem has to do with retirement. Remember, well, here's what the agenda notes I took this morning. Where'd they go? We'll talk about the number of stars in the universe in a second, and that's leading to future topics. But here's an important question. How many of you have jobs, earning some money? Have you done any investment? Good. Yeah, I remember when I was working, my first job was at a hardware store. And I discovered the bank across the street would give you free stuff if you had a deposit of more like $200. So I would save up my checks till I had that $200, and then I'd get my free stuff. Sometimes it was a little trinket. Sometimes it was a cool hat. I did not leave it there, though. I had expenses. I didn't leave it there as an investment. It was more get free stuff for a certain size deposit. I learned as I got a job and had some money that I could put away. This whole 401k thing is a really good thing, but it takes a little thinking and thinking long term. You're going to want to retire sometime. You're kind of young. You're not thinking about retirement, unless maybe you are. Maybe you think, I want to work 20 years. I'll get a really good job. Retire on what I have. Well, in order to have something left in retirement, if you invest just $1,000 in some sort of 401k, even if you don't keep adding to it, like you should be doing if you have a job, keep adding to your 401k. Just $1,000 invested at 5% interest, which is, I'd say, pretty conservative. It's kind of, we don't know what interest rates are. Sometimes they're great, like 20, 30%, depending on your investment. Sometimes it's negative. Sometimes it's, maybe your average is around 5%. And let's see, you're about, 20, maybe you have started investing or invested at 25, retire at 65, so 40 years, $100,000 at 5% interest. We'll take a look at how much money that would be. Sad thing about it is inflation also kicks in. So even though it looks like a lot of money, in 40 years, things are going to cost a lot of money. So we'll keep that in mind. But an investment and continual investment can give you a decent retirement if you plan ahead. And that's an exponential function that is very, very practical in your life. And they actually look at that, but let's think about what exponential functions are. Things like, things we've looked at already, like our the population of the city is decreasing by 200 people each year. When will the population be a certain amount? Well, that's a linear function. We know that each year they're leaving at so much, and so 3 times, in this particular function, 3 times whatever my input is, plus some constant, I get a linear function. But when we talk about population growth, about investment growth, you don't say our population is decreasing by 100 each year. You say our population is decreasing or increasing. We're decreasing by 1% each year. That's a more realistic thing, because as people leave, another 1/10 of the, or 1/100th of the next year, people leave. So that's an exponential function, much more realistic when you're talking about things like population, spread of a disease, investment increase, a chemical experiment that is reacting, certain percent reacts, and you have something left. Aging of anybody in geology, determining the age of rocks is based on the amount of radioactive material. Decreases by a certain percent each year, and we can calculate what the age was. Anyway, those are all exponential functions. Things are multiplied by the previous result. And Sometimes it's either growing or decreasing very rapidly. For investments, we love that. Sometimes there's exponential decrease in something. But the whole point is exponential function looks something like a number to a power of x. Instead of the linear, oh, I'm just multiplying x by a number. Exponential is I'm taking some number, taking it to the power of x. And let's just go over to our friend GeoGebra just to see what they mean by that. So I'll go to geogebra.com. GeoGebra. Why is it responding so slowly? Maybe I shouldn't use Edge when I go to GeoGebra. When I start typing letters, oh, I know what. My little pad here is getting a button clicked when I click on my keyboard, making it do strange things. Here we go. GeoGebra. There. Oh, I should have hit the .com. There we go. I go there, and let's put in an exponential function. Take me there. Come on, just take me there. And start the calculator. And let's look at the function 2 caret x. Enter. That is the function 2 to the x power. And look how that grows. As I zoom out, look how quickly that grows as 2 gets even to the, as x gets to 5, how quickly that goes. Much quicker than x squared. But x squared does a pretty good job of going up rapidly. So that's an exponential. Let's try 1.1 to the x power. It doesn't grow quite as rapidly, but after a while, there it does start to grow rapidly. So that's exponential functions, their general shape if I have a positive number there. And let's try a negative number. Negative 2 to the x. That gets rather interesting as well. Okay, back to our exponential explanation here. Remember, in exponential, we're going to discuss various rules about exponents. Remember that whenever I see this, let's do an example. A squared times a cubed. Remember, a squared is the same as a times a. And a cubed is the same as a times a times a. So these two multiplied basically give me 5 a's multiplied together, and we see that as a to the 5th. A to the 5th. So the rule is, if you have the same number to a power times that same number to a different power, we simply add those together. Because it's like, oh yeah, we have that many a's multiplied times that many a's multiplied gives me x plus y a's multiplied together. So that's our very first rule, called the product rule of exponents. The quotient rule. Oh, and then for your worksheet, all I did in the worksheet was those inverse. Maybe if we come across a simple exponent one, we might do some of those just for practice. So hold on to your papers as we do a little more practice, because I want you to be able to take your notes. Remember, you can bring your laptop if you want to take your notes on that PDF file, if you find that that's handy. The quotient rule. Again, you already know this, but they spell it out very carefully. When I have a, let's do that same thing. A squared divided by a to the 3rd is the same as a times a divided by a times a times a. Well, I can factor out these two a's. They turn into a 1. These two a's get factored out by that. That turns into 1 over a. Or a to the negative 1, which is the same as subtracting, doing a difference of the a's on top minus the number of a's on the bottom. Gives me, in this particular case, a to the negative 1. That's why we're subtracting here in the quotient rule. Think of, oh yeah, that's the same as a to so many multiplied by itself. So many xa's multiply themselves, divided by y's multiplied. Well, if x is larger, then I'm going to have a to some power, because I've divided out all the extra y's and left with a on the top. If y is larger, I'll have more a's left over on the bottom when I factor out all the a's from top and bottom. And remember again, it has to be the same number. A, that's not the same as a to the x over b to the y. I can't simplify a to the x over b to the y. Because a and b are different numbers, I can't do anything more with that. It's only when I have the same number to some power divided by the same number to some other power. And when I have a to the x, the quantity, to another power, I don't add the x and y in this case. I multiply x and y in that case. So, for an example, a squared to the third power is the same as a squared times a squared times a squared. That many times, which gives me a to the 6. So a squared to the third power is 2 times a to the 2 times 3. Little examples, that helps me to solidify it. Yes, I understand why that rule is true. Now, when you, and again, that's the any number a. Now, if you have two numbers multiplied together, and then that taken to a power, that's the same as multiplying the first number by itself so many times, and b by itself so many times. So, for example, ab to the third power is the same as ab times ab times ab. And you see that, oh yeah, that's a to the third times b to the third. Or that part. So a to the third times b to the third. Two numbers multiplied to a power gives you that. That's the power product rule. And when we're solving problems, sometimes we need to, when we're simplifying it, we may go either direction in our finding a way to solve for x or y. Since we can do this, that applies to the same thing to fractional numbers. Different numbers, a over a and b, take it to some power. That's the same as multiplying that one that many times by itself, divided by that one that many times by itself. Just a few more rules, and then some problems that we then use those rules to solve. Any number, for any number a to the 0 power, that's equal to 1. That's basically saying a multiplied by itself 0 times. Or a divided by a to the first divided by a to the first is equal to, using the quotient rule, a to the 1 minus 1 equals a to the 0 equals 1. So a to the 0, it's not 0, it's, think of it as a to the 1 divided by a to the 1, or 1. And a to the negative power is the same as 1 over that. Whenever I do roots, here's maybe a way to simplify this is a to the 1 over y is the same, well, is defined as the y root of a. And if that number that I'm taking to the power of 1 over y happens to be a to the x, well, then I throw a to the x inside the y root, the fractional exponent. We're not going to do a lot of these, but there will be a few that we want to be familiar with, basically handling exponents. Now, in real life, you run across exponents, so the whole deal with doing this in college algebra is to get you familiar with this math, not making you an expert at it, but if you see problems, you'll recognize, oh yeah, there's these basic rules. I can look at that problem and understand what's happening. We'll hand it off to the math nerd to make sure we got the answer right. Okay, so let's do a few problems using exponents. and then see how we did it. The answers are below, but let's do it ourselves first. And if you'd like to put this on your practice worksheet, you can. Otherwise, put it in your notes, because practicing on your own. Let's see here. This one key thing here is it has to be the same number. So it has x and x. Well, remember the product rule. X times itself that many times x times itself that many times is x times itself 2 plus 5 times equals x to the 7. 2 plus 5. The product rule, when they're multiplying, we just add the exponents. When we're dividing, this is the same. Like you can think of this as the same thing as y to the 7th times y to the negative 3rd. You could use your negative exponent rule, remembering, and then I can use the same, hey, I add them together to figure out what the answer is. Or you can jump right to the exponent rule, that when I see a to the x over a to the y, I'm subtracting the bottom from the top. So that equals y to the 7 minus 4. 7 minus 4 equals y to the 3rd. Remember your exponent rule. Think of this as x squared times itself 5 times. So x squared times x squared times x squared. And that means we multiply 2 times 5. We don't add 2 plus 5. We make that x to the 2 times 5 equals x to the 10th. X to the 10th. Now, it gets a little more complicated here. Let's do the inside first. Don't even worry about that negative 1 yet. X to the minus 3 y squared. Well, they're two different numbers. I can't simplify this anymore. But I know negative 1 means all of this goes underneath the 1. 1 over x to negative 3 times y squared. But I can see that 1 over x to the negative 3 is the same as x to the 3rd over y squared. I could have done it here a different way. I could say, well, let's use this rule. Where's that rule? This rule here. We can say, actually, it's kind of a combination of this rule and this rule. I can say x to the negative 3rd to the negative 1 times y squared to the negative 1. So I can use the power product rule and also get me x to the negative 3rd to the negative 1. That's multiply those two together, gives me x to the 3rd. 2 times negative 1 gives me y to the negative 2. And I remember y to the negative 2 is the same as 1 over y squared. Sometimes you like it in this form. Most of the time you like to see it with positive exponents. But both are correct. Sometimes they'll say, give it as a reduced fraction with positive exponents. Then we'll have to give it in that form. So using the power product rule, or seeing, oh, I see that's all of that underneath the denominator, and I know 1 over x to the negative 3rd is the same as x to the 3rd. Multiple ways to get you to the answer. That's what I find the fun part about math, is finding out what's the shortest way. What's the way that will keep me from messing up when I try to solve the problem. Let's see if we got the right answers. Add the exponents gets me the 7. Add the exponents gives me the 4. Wait a minute. You didn't catch me. I messed up right there. That's x, y to the 7th minus 3. I messed up right there because I threw a 4 in there. Oh, man, wasn't getting too sleepy this morning. Y to the 4th. X squared to the 5th, multiplying because we have those parentheses in there. Here, they used a couple rules. to get to their final answer. Oh, and I forgot that last one. Doesn't matter what number is here. Any number to the 0 power gives me 1. I could have had any symbol there. Doesn't matter. I have it to the 0th power. So yeah, I messed up right there. And I switched a 4 for a 3. But that's the basics of the exponentiation. A little practice with that. We'll just make this familiar. That's the whole point here. We're not going to give you super hard problems like word problems. Give you a few just to connect this to the meaning for exponents. Now, as we think about exponents, there are certain rules that we have to follow for the math to work out. And this is not, I guess I'm stuck at that zoom level. Remember, any exponential function will have this form. Some number times some other number. And remember, when you see that x, and there's no parentheses in there, that means it's only b to the x, not a. A is just multiplying, taking b to some power. But we got to pay attention to a few rules about this. That we want the input, the domain of f, is all real numbers. So no imaginary numbers allowed. That's what we've been working with so far. The output, the range of x, is positive, real, when a is greater than 0. So we need an a greater than 0. Then we're always going to have positive numbers. So think positive numbers, we think 0 all the way out to infinity positive. If a is less than 0, I have some negative number times b to the x, then my output, my range, is negative real numbers. And when I think negative, I think it does not include 0. 0 is considered mathematically positive. The Y-intercept is 0a. How do I know that? Well, when x is 0, b to the x is 1. Therefore, I'm going to get the y. So let's just do that. A, b to the x, when x is 0, a, b to the 0, what's my y-intercept? Well, b to the 0, no matter what b is, when x is 0, I'm going to get a. And that's what this is saying. The y-intercept is 0a. So we have a few graphs of an exponential function, and we saw GeoGebra doing that for us. So given these rules, let's look at a few questions here. Which of these functions are exponential functions? Remember, exponential means it's in the form of a, b to the x. Okay? Is this an exponential function? 5x to the x minus 2? Sure looks like it. Well, we can remember that that's the same as 5 to the x over 5 squared, or 5 to the x over 25. Wait a minute. I've got x to some power third. Nope, that's not in that form, b to the x, so not that one. This is some number to the x power. That would be my b, so b is 1/3. A is 1, so that sure looks like exponential. -2 to the x power. To think about that. 1 to the x, well, that's some number to the 0th power. I don't think for that one. Let's see what they say. And they'll explain it why. X to the third is the base. No, b is not. And d is not. And here's how they explain it. It's a negative number as a base, and the base must be a positive number. I've got a little problem with that because I could say this is the same, well, yeah, I have to have, if I had a as a negative 1, that's not the same as negative 1 times 2 to the x. That's not the same thing. That's why this does not count. The base cannot be a negative number. Do they say that up there in the rules? That b must be a positive number. Yes, b here, I skipped over that. b is a positive real number and not equal to 1. Because 1 to any power is always 1. It's meaningless. That is one of those rules I kind of skipped over. I looked at these and I forgot. Yes, b must be positive and not equal to 1. That disqualifies that one. And it also disqualifies that one. Although mathematically, taking a negative number to a power does give you a function. The exponential functions that we want to have in a general form is b is a positive real number not equal to 1. Now let's evaluate some things just using our calculator. And I found a calculator online. That old GeoGebra place gives me a calculator. Let me go grab that and move it to a separate page here so I can do my calculator part. That's at the bottom of every GeoGebra page. So, it won't let me get to the bottom. I guess if I zoom out enough, oh, I had it on my other page. Does it not like Edge? Oh, it's on my other page. Let me get it over on a different website. Why did it go? Let's see. Maybe I can't do that. Let's try. Let's go back to GeoGebra. There. I don't know why it wasn't. The graph wants to take over, and it's not letting me resize my graph. That's what's happening. There. My calculator's down there, but it's hiding. Do I have? Oh, I have to click the little. There we go. There's a little button down in the lower left that brings up your calculator. There we go. There's my calculator down there. And let's put that over to the side here. See, okay, my calculator doesn't disappear. And the problem I'm looking to solve is that one right here. 3 times 2 to the 3x minus 1. Evaluate when x is equal to 2. Well, we can do this by hand to simplify it a little bit, I guess. 3x minus 1, when x is equal to 2, gives me 6 minus 1, gives me 5. So then I can do 3 times 2 to the 5th. And I'm going to use my calculator to give me 3 times 2 to the 5th. Let's see how that's done. With a calculator that has parentheses in it, it's a little easier. And to get that up there it is. 3 times 2 to the 5th, I do 3 multiplied by 2 x to the, do I have that? Oh, I have to do, in this one, I can use the caret symbol. They don't give me the calculator that you might have. In your, oh, here, I think I can do it here. Yeah, right there. I can click on that, and then that tells me what to put in the power part. I put 5, and then I either enter or equal on your manual calculator, and you get the answer 96. If you're a nerd like me, you remember that 2 to the 5th is 32, and 32 times 3 is 96. But just use your calculator. Don't worry about memorizing those power tables unless you have insomnia or something. Good to learn that stuff, but most of us nerds have done that a lot. That's just, our brains just love this stuff. Now we have a problem that looks kind of scary, but all we do is take the numbers they give us and plug them in where they belong. We're given this equation, and this is the one that relates to your investments, your 401k, your payment on your house, your payment on your car. This is the stuff that the bank just tells you, pay this much money. Knowing the formula, you might actually be able to catch them at not giving you or charging you too much, or you find it in a mess, and that's really helpful. But given this, let's just read what this means. A to which a principal will grow after 2 years. So this is the amount of money I'll have in my retirement account, A, after I start with a principal, P. That's what accountants call the amount you started your initial investment at. That's your initial investment, P. T is the number of years. Interest rate is R in decimal form, like 1% is equal to 0.01. That's what they mean by in decimal form. Compounded n times per year. And this was where the banks make it seem really cool. Once a month, that would be 12 times a year. Once a quarter, 4 times a year. Continuously, that's a whole other thing we'll be getting into in a little bit. So now I have all my numbers. I know what n is. So for this particular problem, let's see. We know what r is. Let's make that 0.039 in decimal form of 3.9%. Interest compounded quarterly, that means n is equal to 4. This is the initial deposit, $7,000, that's P. And how much will she have after 5 years? T is the number of years, so T equals 5. Now, with knowing all my numbers, all I do now is plug that in the formula. So I get P, 7,000, times, in parentheses, 1 plus R is 0.039 over n, which is 4, to the 4, that's n, times t, 5 years, 4 times 5, not 45. So make sure you remember that's 20. I'll simplify that to 20 right away before I mess up. Now I just plug that into my calculator by bringing up my calculator online here, and I'll move it to the other side of the page, and plug in these numbers. 7,000. And I don't have to do an asterisk with the calculator. I just start the parenthesis. Implies there's a multiplying there. 1 plus, oh, why does it keep getting bigger? Oh, again, my little button on my pad down below was getting pressed. 1 plus 0.039 divided by 4. Come out here, finish my right parenthesis, and we're taking that whole thing to the 20th power. I hit enter and I get a number, 8499. Just crank it through that formula. And in your programmable calculators, you can actually make that a calculation in this form. And I think they show that in the textbook here. Right here. Plug that into my calculator. It looks a little weird on my calculator, but finally get the answer, 8499.15. So after 5 years at a measly 3.9% interest, 5 years I've earned almost $1,500 on that investment of $7,000. And what's cool is, in another 5 years, it's going to be even nicer. Let's go, well, won't worry about that. But another 5 years, that 5 is going to turn into a 10, and that number is going to be very nice. But you have to wait 10 years, and inflation is also chasing you. If inflation is at 3.9%, you're just keeping up. So remember, when you're doing that investment, part of it is to keep up with the prices are going to be increasing in the future. You want an investment that's more than whose interest is more than inflation. And usually they are, because people that you invest with usually are smart enough to beat inflation. Now they give you another formula. The formula becomes compounding interest, where R, that's the rate, is 100%. Well, that means I'm adding that much every n times per year. it becomes a simpler formula in this thing when I'm compounding interest. We come across a very special number as n gets really big, like as it approaches infinity. And that's where the number e comes from, which we'll be dealing with when we deal with logarithms. But this is a little to the side that when n gets really, really big, like I'm calculating it continuously, I can calculate my continuous interest. I have a simpler formula involving that special number e to the rate of return times the number of years. All this to say is most banks are using continuous compounding. They want you as a customer because it gives you a tiny bit more money, and they use that as an advertising gimmick. E to the RT. Simpler formula than this. When I'm compounding it once a month or once every quarter, I have to use this formula. But most banks, when they say, we're compounding continuously, you might ask them that question. You can use this formula. And E is such a famous number, it's programmed into your calculator. So here's a formula you can use when we have continuous compounded interest. Again, I'll call it a famous exponential function that is used all over business. So the point here is exponential functions are important. Here's one very famous one. There's lots of other exponential functions, and now we'll practice with some simpler ones. But let's just say we're given that formula, and we want to now solve for a particular problem. We have to just know what A, P, R, and T are, and I can solve my problem. So, they ask you for two answers. Semi-annually, well, that means I have to use that original formula that my value is going to be my original investment, P, that's $10,000, times 1 plus, what was it? R over N, 4%, 0.04 over N. Semi-annually means we are calculating it 2 times a year. And T is 10 years. T is 10. 2 times 10. Plugging that in gets me down to this formula. I plug that into my calculator, and I see that an investment of $10,000 only compounded or recalculated every 6 months, I'll have a value after 10 years of $14,000. Not bad. But the bank will say, wait a minute, we'll give you compounded continuously. Let's see what that number would look like. Well, continuously, I would use this formula. My value after 10 years will be my principal, $10,000, times E, which is a special number. We have our calculator know what it is, times R, that would be 0.04, times 10 years, or E to the 0.4, 10,000 E to the 0.4. What number does that give me? Let's find out. I'll just sit down here. They calculated it for me. A tiny bit more. What is it? Almost $60, maybe. Yeah, about $60. About $60 more after 10 years. Not a huge difference. So although they'll say, hey, we do compounded continuously, you don't earn a ton more, but it's enough to say, okay, I'll go with you. I like compounded continuously. And to the bankers, they just plug it in a calculator. When you come to they send you your statement. They just use one little calculator in there. Their computer calculates it, puts it on your statement. Just using that formula. So a very important formula to anyone doing investment isn't super complicated. principal times E times the rate I'm earning times the number of years. This applies to mortgages, to most investments. They're either charging you interest or hopefully in you getting a good job, with your degree you're getting, you will earn money and invest it at an interest. One thing to remember, if you have credit card payments, what's the typical interest on a credit card? 10%? That's a tiny amount. Most credit cards are up around 20%. So watch out for that. They'll give you a good deal. They'll say, you get our credit card, 0% interest for 6 months. You pile up the debt, and then comes the 20%. And that number gets them a lot of money from you. The only people that can spend money and not pay back and not have their credit rating go down is your government. You have to be responsible and pay off those credit cards, or this will become your debt. We don't like those high numbers in your debt. So one lesson here, even if you don't remember all this compound interest stuff and exponential functions, remember interest makes things grow really fast as time goes by. So if you have a balance in your credit card, your payments will go sky high if you don't pay off those credit cards. Mortgage as well. $200,000 house, pretty decent in Dubuque. In Denver, $200,000 house is like a tiny house. I learned that from a guy wanting to move to Denver. He decided not to move from Dubuque because houses there are like 10 times the price of houses here. He couldn't afford it. Payments on those things. You look and say, you get the little statement, yeah, after you paid off your mortgage on your $120,000 house, you will end up having paid us $300,000. It's like, whoa, really? Well, I don't have the cash. I don't have the $120,000 cash. Either we go to a smaller house. Dave Ramsey says pay off that mortgage because those numbers get big. We don't want you to be stuck in debt. Okay, let's do a few little calculations here just for fun. Function e to the x. Well, f of negative 4 means e to the negative 4. Let's just use our calculator. I think I have an e in here somewhere. There it is. E, take it to the power of negative 4. Enter. And I get 0.0183. Write that down using my calculator. When you get to things like this, don't worry about calculating. Just plug it into your calculator. You can estimate after a while. Uh-oh. This is not so bad. Let's do this piece by piece. F of x equals 6 to the 2x minus 3. So f of 1 is 6 to the 2 times 1 minus 3 equals, well, 6 to the 2 times 1 minus 3 is equal to 6 to the negative 1. Oh, I can do that in my head. Equals 1 over 6. If I want it in my calculator, I'll go to my calculator, type in 6, and is there a 1 over x, or do I do a 1 divided by x? Some calculators have a 1 over x function. I don't see that in mine, so I'll just do a back up, and I'll do a 1 divided by 6, and enter 0.16666 forever. Calculator, 0.166, and to designate 66 going on forever, you just put a little line over that. If I want to round it to 4 decimal places, then I would do 0.1, 1, 2. This would be my 4th decimal place. 66 rounds up to 7. So 4 decimal places would be that. F of 2, oh, not too bad. 6 to the 2 times 2 minus 3, or 6 to the 4 minus 3, that's a minus there, 6 to the 4 minus 3, or 6 to the first power equals 6. Oh, easy one. Compounded semiannual. Okay, they threw that little compounding formula at us just to give us a little practice at understanding that formula. And I'm just going to write that down. The value of my investment is equal to my initial investment, P, times 1 plus, if I remember right, is the rate divided by n times nt. Let's just check that I got that right. R1 nt. Okay. All we do is plug in our numbers. So we do 3300 times 1 plus 0.045 over semi-annually. That means twice a year, 2. So that means n equals 2. To the power of, well, 7 years, 2 times 7 years. Simplify some things here, or, yeah, I'll make that, that's equal to 14. Plug the rest into my calculator, bring it over here, put it over here on the right. Will it shrink on me? Let's see. Plug it in. We'll do the 3,000 times, left parenthesis, 1 plus 0.045 divided by 2, parenthesis, and the right arrow, make sure I get out there, and take that to the power of 14. So 1 plus a very small number to the 14th power will grow a little bit. Let's see how much it grows. So 7 years, $3,000 investment. I'm guessing maybe 4,100. Let's see what we get. Enter. Oh, 4096.4501. What's that?
You put the 3,000 instead of 330. Well, 3.
Uh-oh.
300.
Oh, in my calculator.
Yeah.
Oh, I see, right there. Oh, very good. Thanks for catching that. Now it's going to be more, right? So 3,000, but 3,300 should give me probably 4,200. Let's see what we get. 4,500. So that $300 grew a little bit more. And the more you start with, the more you'll have at the end. The key is this number here is bigger than 1. If this is smaller than 1, I am shrinking my investment. I am losing money over time. So you don't want that kind of investment. You want an investment that grows. So your rate here needs to be a positive number. And that's the risk you take. You invest in Bitcoin. Over 2021, it's been a big number. But 2021 to 2022, maybe it's going to be a smaller number. Or a negative number. So right now it's worth about $50,000 per Bitcoin. At the end of 2022, it might be 10,000 or it might be 100,000. That's the scary part. So don't invest in Bitcoin. It's a big risk. Unless you have money that you can afford to lose, don't buy Bitcoin. Some investments are even worse than that. If you invest in something, you can actually owe money if you invest in certain things. You can have a negative return rate. Most investments, well, I either get something or I lose it all. Some things you can invest, like futures, you owe big time. Don't invest in those things unless you can really have afford it. Question?
Yeah, are we turning these in?
Yeah, just turn it in. That'll just count as attendance. And it'll help me if you have any problems with any of those. Like, I sure wish we could go over this particular one. I'd be happy to take your input and help you with that. I'm going to save this to the disk, and I'll upload it for your review. You're not required to view it.